Here are the sample problems for Math 117, Class 15. So a lot of times you want to take a random variable x, multiply it by some constant alpha, and then add another constant beta. And the question is, if you know the density function for the original capital X, how do you get the density function for this new random variable? We're going to solve that problem in general. And the way to do it without ever taking any derivatives is to write down the probability that this random variable lies in an arbitrary closed interval from a to b. In other words, the probability for the set of elements of our sample space where, on the one hand, alpha x plus beta is greater than or equal to, not alpha, but a, and on the other hand, is less than or equal to b. And the usual thing you do here is you transform the inequality until eventually you've got an x in the middle. So this is, of course, the same as the probability that alpha x is in between a minus beta and b minus beta, and it's also the probability of the set of elements in the sample space for which a minus beta over alpha is less than or equal to x, which in turn is less than or equal to b minus beta over alpha. And now, assuming that x is completely described by a density function, this is the probability that x is in between a minus beta over alpha and b minus beta over alpha, which in turn is the integral of the density function from a minus beta over alpha to b minus beta over alpha. And because I want to reserve x as my final variable of integration, I'm going to write this as an integral over y. That means I can now set y equal to x minus beta over alpha, and therefore dy is dx over alpha. So this integral expressed in terms of the new variable of integration x is an integral that just goes from x equals a to x equals b. We've got this 1 over alpha here, and we have f sub x of y, which turned into x minus beta over alpha dx. So that proves the result. This means whenever you've got a distribution like the normal distribution that's described by its density function, you can figure out the new density function for slightly modified versions of that variable. And that brings us to the second part of the problem. You're playing a game, you roll a fair die 100 times, and the deal is if it comes up 6, you win $6, otherwise you win nothing. So let's think about the random variable that describes the ith roll, x sub I. The expectation of that random variable is the probability of 1/6 of getting $6 times $6 or 1. And the variance is, as you now know, the expectation of the square of the random variable minus the square of the expectation. So that's 1/6 the probability of getting a 6 times 6 squared. And we have to subtract off the square of the expectation 1. That's 6 minus 1, or 5. So for an individual roll, we have an expectation of 1, a variance of 5. The sum z of 100 independent rolls has an expectation that's 100 times bigger. It's 100. And because the rolls are independent, it has a variance that's 100 times bigger. In other words, z is approximately normally distributed with an expectation of 100 and a variance of 500. That's basically what the central limit says, theorem says. If you add together a large number of random variables, all with the same distribution, then you get a distribution with a variance that's the sum of the variances, an expectation that's the sum of the expectations, and it's approximately a normal distribution. How would we make this? Well, in order to multiply the variance by 500, we'd have to take a standard normal random variable and multiply it by the square root of 500, and then we would have to add on 100 to that to change the expectation from 0 to 100. And this is correct where x is a normal distribution with 0 expectation and variance 1. But for that, we know the density function. It's the square root of 1 over 2 pi times e to the minus x squared over 2. And using the formula that I just proved, I can say, therefore, the density function for the new variable z is 1 over 2 pi. And then we've got this 1 over alpha. Alpha was the square root of 500. So we've got the square root of 1 over 500 times e to the, now comes our f sub x of x minus beta over alpha. So the exponent is x minus 100 squared over 2 times 500, or 1,000. So that's the approximate density function for this. And that's how to use the central limit theorem to concoct density functions in new situations. We move along to the next problem. It's another one where you're inventing new density functions from old, and this time you know the density function for x and for y, and you need the density function for x plus y. And the way to do this is to, again, start by computing the probability that our new random variable is less than or equal to some value z. No assumption here that x and y are necessarily positive. So here is the line z equals x plus y. And if I go up to a certain value y, I can say that the corresponding value of x has to be z minus y. Now what am I going to compute? I'm going to compute the distribution function f sub z of little z, and that's the probability that the sum of the two random variables x and y is less than or equal to z. Once I've got that figured out, I'm going to take its derivative to get the density function. So now I have to integrate over the entire plane, and I'm going to integrate first over x. And I'm trying to hint here that I'm doing an integral over a strip that extends all the way from minus infinity up to this line. And then, once I've done that integral, I'm going to do a second integral over I to complete the integration over the whole plane. So, the distribution function is the result of integrating over y from minus infinity to infinity, the result of integrating from minus infinity to z minus y, that's over this strip, the density function for the random variable x, having done that, I multiply by the density function for y and integrate over y. Now, in this case, the integral over x has a limit of integration that depends on y. That's a nuisance to deal with, so I'm going to get rid of the problem by just making a change of variable in the inner integral. I'm just going to set x equal to w minus y, and now my integral for the distribution function looks a good deal more manageable. I'm integrating over y from minus infinity to infinity, and I'm integrating over w just from minus infinity to z. Z is a constant for purposes of this integral. I've got f sub x now as a function of w minus y. I multiply by the density function for y and integrate over y. Now what I'm integrating in over is a rectangle. And I'm just going to reverse the order in which I integrate over the rectangle. What I'm going to do is my second integral is going to be over w from negative infinity to z. My first integral is going to be the integral from minus infinity to infinity of f sub x of w minus y times f sub y of y, that integral being done with respect to y. And after I've done that, I'm going to integrate with respect to w. But I'm not interested in capital F. I'm interested in little f, which is the derivative of capital F with respect to its argument. Remember back in your first calculus course when you were doing a derivative with respect to a limit of integration? What's the rule? The rule is, in this particular simple case where the variable with respect to which you're differentiating is just the upper limit of integration, is you evaluate the integrand at the upper limit of integration. This is an application of the fundamental theorem of the calculus. So what's the derivative of this with respect to z? It is the inner integral evaluated at the upper limit of integration, which means I replace the variable of integration w by the constant z, and presto, I have proved the convolution formula. And when you think about it, this is fairly reasonable. You take the probability for the random variable to be in a small interval around y, multiply it by the probability for x to be around the value z minus y that makes the sum equal to z, and then you sum up over y. So that's the proof of the convolution formula. By the way, there are other equivalent convolution formulas. This is just the best known of many of them. Let me lean up the screen. Come on. F, little f, there you are. And finally, nope, set, capital F. Okay, 2 down, 2 to go. You've been doing problems like this next one for a while, but now I'm introducing formally the concept of Lebesgue measure. When I say the probability is specified by little l sub 0, 8, that just means that the probability for an interval specified by a lower limit a and an upper limit b that are both in between 0 and 8 is the length of the interval divided by 8. So this is formalizing the concept we've had all along. The probability that a random variable is in a certain interval is proportional to the length of that interval. In other words, the probability that random variable x is less than or equal to little x is just x over 8, and the density function is therefore 1/8, the constant that integrates to 1. Now what about our other random variable y? We've defined a new random variable y to be the cube root of x, and now I'm going to show you a trick that I think is starting to get familiar. To get the distribution function, I say, by that I mean the probability that capital Y is less than or equal to little y, or if you prefer, the probability that the cube root of x is less than or equal to some real number y, which is in turn just the probability that x itself is less than or equal to y cubed. And since we know the probability distribution function for x is specified by Lebesgue measure, this is y cubed over 8. If I want the density function, I just take a derivative, and I get 3y squared over 8. This always looks like black magic to me, so I compulsively check it. If x can be between 0 and 8, its cube root can be between 0 and 2. So as my check, I integrate from 0 to 2 this density function with respect to y. The antiderivative is y cubed over 8. And when I evaluate that between the limits 0 and 2, I do indeed get 1. Now, what I want to do is calculate the expectation of a function of my original value, random variable. I want to calculate the expectation of x to the 2/3. And there are two ways of doing this. The easiest way is just to use the original sample space and say the function of the random variable we're calculating is x to the 2/3. For each value of x, we take that, multiply it by the density function, which has the constant value 1/8, So the antiderivative is 3/5 times x to the 5/3. Conveniently, 8 to the 5/3 is 32, so I get 3/5 times 1/8 times 32, which is 12/5. And just to prove that it can be done, I can get the same result using my new random variable y. In this case, the random variable is written in terms of y as y squared. So what do I do? Well, y ranges from 0 to 2. My function of y is y squared. I multiply that by my density function, 3y squared over 8. And what do I get? Well, I've got 3. The antiderivative is y to the 5th over 5. The limits of integration are 0 and 2. So that's 3 times 32 over 5 times 8. And what do you know? It's 12/5 again. This last calculation can be done more generally, but even the simplest case is messy enough to be a proof that you might want a blackball for the final exam. The challenge is to use that convolution function formula that I proved earlier to show that if you add together two independent standard normal random variables, you get a normal random variable with a variance of 2. You know that for two independent random variables with variance 1, the result is going to have a variance of 2. And the significant result from this calculation is it's also normally distributed. This will give you some more confidence in the central limit theorem. What this says is once you've got normal random variables and add them together, you continue to get normal random variables. So let's use the convolution formula. Which says that the density function for the sum, x plus y, is the product of the two density functions. Each of those has a factor of 1 over the square root of 2 pi in it. And then the convolution formula says we integrate from minus infinity to infinity. The density function for x, evaluated for z minus y, times the density function for y, and we integrate over y. Good enough. Let's multiply that out. So I've got e to the what? I've got e to the minus, well, expanding z minus y squared. I've got z squared over 2 minus zy plus y squared over 2. And then I've got another y squared over 2 from the second exponent. Now comes the trick. Remember back in middle school when you were learning the quadratic formula and you had to complete the square? Basically, that's what we're going to do here. So that exponent has y squared minus zy plus y squared plus z squared over 2 in it. Well, if I want to get y squared minus zy, I need to take y minus z over 2 and square it. That'll give me that term and that term. But it only gives me a z squared over 4. So I have another factor of z squared over 4 added on. And now I can write this density function in a more manageable form. 1 over 2 pi e to the minus z squared over 4 from this term goes outside the integral sign, and then I have something that depends on y, the integral from minus infinity to infinity of e to the minus y minus z over 2 quantity squared with respect to y. Now the only integral of this form that I know how to do is e to the minus x squared over 2. So what I will do is take y minus z over 2 and set it oh so cleverly to x over the square root of 2, so that dy is dx over the square root of 2. And now the density function is equal to, well, I've got this 1 over 2 pi. I'm going to split it up into two factors of the square root of 1 over 2 pi. I've got e to the minus z squared over 4 sitting outside, and then that all gets multiplied by another 1 over the square root of 2 pi times the 1 over the square root of 2 from there times the integral from minus infinity to infinity of e to the minus x squared over 2 dx. Well, if I didn't have this 1 over root 2, this would be exactly 1. Because of that extra factor, I get 1 over the square root of 2, and there's my answer. I've got 1 over the square root of 4 pi times e to the minus z squared over 4. And what's that? That's the density function with sigma squared equals 2. That's the density function for a normal distribution with expectation 0 and variance 2.